Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. During this session, we are going to discuss on Boolean algebra. What is Boolean algebra? It deals with algebra of binary numbers, zeros and ones. It helps in designing logic circuits used in processors. An electronic circuit or switching circuit can be described by a Boolean expression. Today, designers use Boolean algebra extensively in assigning electronic circuitry of computers. Yes, it is the fundamental concept in the development of digital circuits. Boolean algebra was developed by a famous English mathematician, George Boole, in mid-1800. Let's see what are the fundamental concepts of Boolean algebra. I know you are familiar with elementary algebraic expressions in decimal numbers. Such an algebraic expression will have many variables and each variable can take any decimal numeric value. For example, if you consider an algebraic expression x plus 3y equal to 10, both x and y can take any decimal value that satisfies this equation. In Boolean algebra, the only numbers we use are zeros and ones. Because Boolean algebra deals with binary numbers, and so the variables used in Boolean equation take only two values, 0 or 1. These variables are called as Boolean variables. Consider the term x plus y. Both x and y can take only the values zeros and ones. So, the maximum possible combinations of x and y are 0, 0, 0, 1, 1, 0 and 1, 1. You may recall from the previous sessions that in a binary number system for n variables, the number of possible combinations will be 2 raised to n. Hope you understood that Boolean algebra deals with binary numbers and Boolean variables take only two values, either 0 or 1. Then, what are the different operations that can be done on Boolean variables? The three important operations are logical addition, logical multiplication and complementation. Let's have a discussion on each operation. The first one, logical addition. It is also known as OR operation and is represented by the symbol plus. We can define plus operator or OR operator by listing all possible combinations of A and B. In the table shown here, we have given two inputs A and B and all possible combinations of its values 0, 0, 0, 1, 1, 0 and 1, 1. And also the result is given. Now observe the result. The result is 0 only when both A and B are 0. That is when all inputs are 0. In all the other cases, the output or the result is 1. This is different from normal arithmetic addition that we do in decimal, and we call this operation as logical addition. Logical addition can be extended to multiple variables too. Notice the table given here. It has a special name, truth table. The table that gives all input combinations and its output values. In other words, it shows how the result or functional value varies with respect to each input. The next operation is logical multiplication or AND operation, and the symbol is dot. We can define the dot symbol or AND operator by listing all combinations of A and B, and C gives the output. Note the point, the result is 1 only when all input values are 1, otherwise the result is 0. The next is complementation or logical NOT operation. The above two operations OR and AND are binary operations because they operate on two variables. Complementation is a unary operation which operates on a single value. We can find the complement of a single variable or of a Boolean expression. The truth table for logical NOT is given here. Logical NOT defines that complement of 0 is 1 and complement of 1 is 0. Dear friends, we shall use the words plus, dot and complement here onwards for the operations OR, and NOT respectively. For the error-free evaluation of Boolean expressions, we must also know operator precedence. When we have more than one operator in an expression, we need to know which is to be evaluated first. We need to know how to group the terms for evaluation. Precedence of operators determines this, and so it is mandatory to know about it. The precedence rules for Boolean operators are given here. 1. The expressions are scanned from left to right. Then expressions in the parentheses are evaluated first. Complementation operations are performed next. Then AND operations, and finally OR operations are performed. Now see the equation given here. How the Boolean expression f equal to w plus yz complement dot x will be evaluated. Scan the expression from left to right. We don't see any parenthesis. Then precedence rule says complement operation has highest precedence than AND. So yz whole complement will be evaluated first. Then we are left with plus and dot, where dot has higher precedence, so yz complement dot x is calculated, and at last the plus operator, that is OR with w. Hope you understood the relevance of operator precedence and how to do it. Moving on to the next topic, let's discuss on postulates of Boolean algebra. What do you mean by postulate? In a literal sense, it is something that is assumed as true as the basis for reasoning. It is the same case here. Postulates are the basic axioms of the algebraic structure. They don't need any proof, rather they are used to prove the theorems of Boolean algebra. The table given here lists out the postulates of Boolean algebra. They are: the first postulate is defined as A equal to 0 if and only if A is not equal to 1, and if A equal to 1 if and only if A is not equal to 0. It clearly states that the variable A can take only two values 0 and 1. The second postulate, x plus 0 equal to 0 and x dot 1 equal to x. See, additive identity is 0 and multiplicative identity is 1. Also, they are dual to each other as for all other postulates. The third postulate talks about commutative law, which is stated as x plus y equal to y plus x. Its dual is x dot y equal to y dot x. The next is associative law, which says x plus y plus z in bracket equal to x plus y in bracket plus z. Here we have only a single operator, even though the terms are grouped in a different manner. On the left hand side, y and z are grouped, whereas on the right hand side x and y are grouped. Both LHS and RHS gives the same result. Its dual x dot y dot z equal to x dot y dot z also exists. Then distributive law, x dot y plus z equal to x dot y plus x dot z, and its dual x plus y dot z equal to x plus y dot x plus z also exists. That is, ANDing a variable by a group of ORed terms is same as ANDing each term separately, then OR them. This is distributive law. And the last postulate states here x plus x complement equal to 1, and x dot x complement equal to 0. A Boolean variable is ORed or logically added with its complement gives a 1, and a Boolean variable ANDed or logically multiplied with its complement gives a 0. You must learn the postulates and theorems thoroughly, which would be helpful while minimizing Boolean functions and expressions. Okay? Let me introduce one more important characteristic of Boolean algebra, the principle of duality. I have already mentioned the word dual. See the table of postulates. We have two columns of data, column 2 and column 3. Consider postulate 2, which is x plus 0 equal to x. The data in column 3 can be obtained from column 2 by interchanging ones to zeros and plus to dot or to and. It happens for all postulates, right? Column 3 is obtained from column 2 content by interchanging ones and zeros and then plus and dot, and the vice versa. This is principle of duality. There is a precise duality exists between the operators and or and the digits 0 and 1. In the same way, you can obtain the dual of any Boolean theorem or postulates. Also, when we prove a theorem, we don't need to prove its dual because it exists. The next topic of discussion for today is theorems of Boolean algebra. Theorems of Boolean algebra are stated in the given table. These theorems are used to simplify or minimize the Boolean expressions. As I mentioned earlier, the dual of these theorems also exists. Each theorem can be proved using postulates and theorems, and let's discuss one or two here. You may please refer to the course page for the proof of other theorems. The first theorem states that x plus x equal to x, and its dual x dot x equal to x. It is known as idempotent law of Boolean algebra. How do we prove this? See, the LHS is x plus x. That can be written as x plus x dot 1 by the postulate 2, that is x dot 1 equal to x, which can again be written as x plus x dot x plus x bar by the postulate 6, which says x plus x complement equal to 1. The next step can be easily deduced using distributive law, that is postulate 5, and the expression can be written as x plus x dot x bar in bracket. What is x dot x bar? It is 0 by postulate 6. So, the term is x plus 0, which is x itself by postulate 2. Hence, the proof x plus x equal to x. The dual of this theorem x dot x equal to x can also be proved by following the same steps, but interchanging operators plus and dot and ones and zeros. The second theorem states that x plus 1 equal to 1 and the dual x dot 0 equal to 0. This can be proved following the steps. LHS x dot 0 equal to x dot 0 plus 0. This is by using the postulate 2, x plus 0 equal to x. Then the expression becomes x dot 0 plus x dot x bar, because x dot x bar is nothing but 0. So, the 0 is replaced by x dot x bar. Again, using the postulate 5, x plus y dot z equal to x plus y dot x plus z, we can make the expression to the form x dot 0 plus x bar. It becomes x dot x bar by postulate 2 and the result is 0. The next is absorption law, which states that x plus x dot y equal to x. Let's try to prove this. X plus x dot y is equal to x dot 1 plus x dot y. This is by postulate 2, which says x dot 1 equal to x. and this expression can again be written as x dot 1 plus y by postulate 5, x dot y plus z equal to x dot y plus x dot z. So, the expression is x dot y plus 1. Now, we can write this expression as x dot 1 by theorem 2, which says x plus 1 equal to 1. And this expression is evaluated as x by postulate 2, that says x dot 1 equal to x. The next is involution law, which states that x double complement is equal to x. That means complement of a complement returns its original value. Please note, the dual of all these theorems can be proved by applying the same principle of duality to various steps of the proof. Now, we have proved these theorems by using the postulates and theorems we have studied so far. You can also prove theorems by using another method, by using truth tables. In this method, we write the truth table of both the sides of the expression, left hand side and right hand side, and check whether it yields to identical result. The truth table is created using all possible combinations of the variable values involved in the expression, and this particular method of proving is known as perfect induction or exhaustive enumeration. We have few more theorems to discuss, and the next is x dot x complement plus y, which is equal to x dot y. And the dual of this theorem is x plus x complement dot y equal to x plus y. Let us prove this theorem by the method of perfect induction. For the same, we have to create the truth table of both left hand side and right hand side. Expressions as given in the table, 0, 0, 0, 1, 1, 0, 1, 1 are the values of x and y. Then in the truth table, we fill the column x complement, then x complement dot y, then x plus x complement dot y, and the final column is x plus y. And you can see that the last two column gives the same values 0, 1, 1, 1. One of the important theorem in Boolean algebra is De Morgan's law. De Morgan's theorem states that x dot y whole complement is equal to x complement plus y complement. That is, complement of the product of all terms is equal to the sum of complement of individual terms. In the same way, x plus y whole complement is equal to x complement dot y complement. That is, complement of the sum of all terms is equal to the product of complement of individual terms. Let us try to prove this theorem, the De Morgan's law, by using the method of perfect induction. In the truth table, we write the two columns for x and y input values, then x complement, y complement, x plus y, and the last two columns are x plus y whole complement and x complement dot y complement. And see the result, both columns gives the same values. It proves the theorem. De Morgan's law can be extended up to n variables. For example, x1 plus x2 plus x3 plus x4 whole complement can be written as x1 complement dot x2 complement dot x3 complement dot x4 complement by applying the De Morgan's theorem. Here we used 4 variables, and this can be extended up to any number of variables. Then we are moving to the next topic, Boolean functions and minimization of Boolean functions. Boolean function is an algebraic expression that contains Boolean variables or binary variable and operators such as or, and not. For example, consider the function a plus b complement dot c. It is a function of 3 variables a, b and c operated with 3 Boolean operators plus, dot and complement. Algebraic expression for a given Boolean function need not be unique always, because you are able to simplify the expression for any given expression. Let us see now how to minimize or simplify a Boolean function. This can be done by applying postulates and theorems in various levels of the expression. We can also minimize the Boolean expressions using K-map, which will be discussed in a later session. Now let's see one example of simplification of a Boolean expression. Given the function f is equal to a plus b dot a plus b complement. The task is to minimize the function. By distributive law, this can be written as a plus ab complement plus ba plus b complement. By applying x dot x equal to x and x dot x complement equal to 0, the first and last terms becomes a and 0 respectively. So, f is equal to a plus ab complement plus ba plus 0, which in turn f is equal to a plus ab complement plus ba, because x plus 0 is equal to x. Again, apply distributive law and commutative law, then it can be written as f is equal to a plus a b complement plus b. As you know, b complement plus b is equal to 1. Then f becomes a plus a, which is a by theorem 1. So, the Boolean function f is equal to a plus b dot a plus b complement can be simplified up to a single variable a. More exercises on minimization of Boolean functions are given in the course page for your reference. Next, we are going to see how to complement a function. If q is a Boolean function, then q bar is the complement of q. The complement of a function can be derived from De Morgan's theorem. Yes, for example, let's try to find the complement of f is equal to x dot y complement plus y dot z. What is f complement? How do you find the complement of this function f? The f complement is equal to x dot y complement plus y dot z whole complement. De Morgan's law states that a plus b whole complement is equal to a complement dot b complement. So, x dot y complement plus y dot z whole complement can be written as x dot y complement whole complement dot y dot z complement complement. Again, use De Morgan's theorem on each term separately, then we get x complement plus y double complement dot y complement plus z complement. From involution law, we know that y double complement is equal to y. So, the answer is f complement equal to x complement plus y dot y complement plus z complement. And you can apply the similar procedure for any Boolean functions to obtain its complement. When you observe closely, you will come to know that the complement is nothing but the dual of the function where each variable is complemented in place interchanging zeros and ones, and or are interchanged as well. So, this is the easiest procedure to derive the complement. More exercises on finding complement of Boolean functions are also given in the course page for your reference. So, in this session we have covered most of the important concepts used in Boolean algebra. We started with definition, then operators, followed by postulates and theorems. At last, we discussed how to minimize a Boolean function and the method of obtaining the complement of a function. Let me conclude now. Thank you for watching. See you in the next session. Bye.